November 1943, Wright Field, Dayton, Ohio. The propeller lay in pieces across the test stand. Its hollow steel blades twisted and fractured from catastrophic failure at 460 miles per hour. Engineers from Hamilton Standard stood in silence, examining the wreckage of what was supposed to be the solution to the P-51 Mustang's final performance barrier. The aircraft itself had proven exceptional in nearly every measure, but at extreme speeds, the standard propeller became a liability rather than an asset. What happened next would determine whether the Mustang remained a very good fighter or became the instrument that would decide the air war over Europe. The problem was not immediately obvious to casual observers. The P-51 Mustang had already established itself as an outstanding aircraft by late 1943. Powered by the Packard-built Merlin engine, a licensed version of the British Rolls-Royce design, the Mustang demonstrated superior performance at high altitude, where the war was increasingly being fought. It could reach speeds exceeding 400 miles per hour, climb rapidly, and maintain combat capability at altitudes above 25,000 feet, where German interceptors struggled. Yet despite these impressive characteristics, test pilots reported a disturbing phenomenon during high-speed dives and maximum power runs. The aircraft became difficult to control, vibrations increased dramatically, and in several instances, complete loss of thrust occurred without engine failure. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The investigation centered on a component that received less attention than engines or airframes, but proved equally critical to aircraft performance. The propeller served as the interface between engine power and flight performance, converting rotational energy into thrust. In 1943, propeller technology had advanced significantly from the fixed-pitch wooden designs of the First World War. Modern fighters employed variable-pitch constant-speed propellers with hollow steel blades that could adjust their angle during flight to maintain optimal efficiency across different speed and power regimes. Hamilton Standard, a division of United Aircraft Corporation, had become the primary supplier of propellers for American military aircraft, producing designs that equipped everything from trainers to heavy bombers. The Mustang's standard propeller was an Aero Products unit, a four-bladed design with a diameter of 11 feet 2 inches. This propeller worked adequately at normal operating speeds and altitudes, but when pilots pushed the aircraft to its performance limits, serious problems emerged. At speeds approaching 450 miles per hour, the propeller tips were moving through the air at velocities exceeding the speed of sound. Supersonic airflow created shock waves along the blade surfaces, disrupting the smooth flow of air and causing dramatic losses in thrust efficiency. The phenomenon, known as compressibility effects, was poorly understood in 1943. Engineers knew that propellers lost efficiency at high speeds, but the precise mechanisms and potential solutions remained subjects of intensive research. Robert Johnson, chief test pilot for the Mustang program at North American Aviation, filed detailed reports throughout the autumn of 1943 documenting the high-speed handling problems. During a maximum speed dive from 30,000 feet, the Mustang would accelerate rapidly, reaching indicated airspeeds above 450 miles per hour. At these velocities, violent vibrations developed, emanating from the propeller and transmitted through the engine mounts into the airframe. The control column shook in Johnson's hands. The entire aircraft buffeted as if flying through severe turbulence despite perfectly clear air. The engine was producing full horsepower, but that power was not being efficiently converted to thrust. Engineering analysis traced the problem to propeller blade design and the aerodynamic forces acting on the blades at high rotational speeds. The Aero Products propeller featured relatively wide blade profiles optimized for efficiency at cruise speeds. This design worked well under normal conditions, but at extreme velocities, the blade tips encountered supersonic airflow. When portions of the blade operated in supersonic conditions, while other sections remained subsonic, shock waves formed at the transition points. These shock waves caused flow separation, turbulence, and dramatic increases in drag. Instead of pulling the aircraft forward efficiently, the propeller blades encountered massive, aerodynamic resistance that absorbed engine power without producing proportional thrust. Hamilton Standard had been researching solutions to high-speed propeller performance since the late 1930s. Their engineers understood that reducing blade width would delay the onset of compressibility problems by reducing the area exposed to supersonic flow. Narrower blades meant less surface area, encountering shock waves at any given rotational speed. However, narrower blades also meant less total blade area to generate thrust, requiring careful optimization to maintain low-speed performance while improving high-speed characteristics. The challenge was achieving both objectives simultaneously, creating a propeller that worked efficiently across the entire speed range from takeoff to maximum velocity. The solution emerged from systematic testing at Hamilton Standard's facility in East Hartford, Connecticut. Engineers designed a new propeller specifically for high-performance applications, featuring blades significantly narrower than standard designs. The blade width at the tip measured just 6 inches compared to 9 inches on conventional propellers. The blades were also thinner in cross-section, using advanced airfoil profiles developed through wind tunnel testing. Total blade area was reduced by approximately 30% compared to the Aero Products design, requiring increased rotational speed to maintain thrust at low velocities, but offering potentially dramatic improvements at high speed where compressibility effects dominated performance. The new design, designated the Hamilton Standard Hydromatic Propeller, incorporated several innovative features beyond the narrow blade profile. The blades were manufactured from hollow steel stampings, a production technique that reduced weight while maintaining structural strength. Internal reinforcement ribs prevented collapse under centrifugal loads, while keeping the blade mass concentrated near the hub, where it contributed less to rotational inertia. The pitch change mechanism used hydraulic pressure from engine-driven pumps to rotate the blades through their full range, from fine pitch for takeoff to coarse pitch for high-speed cruise. A constant speed governor automatically adjusted blade angle to maintain selected engine RPM, regardless of airspeed or power setting, optimizing efficiency continuously during flight. Manufacturing the new propeller blades presented significant challenges. The narrow, thin profile required precise forming operations to create the complex, curved surfaces while maintaining structural integrity. The steel stampings had to be heat-treated to achieve proper strength characteristics without becoming brittle. Internal reinforcement structures needed exact placement to prevent failure under the enormous centrifugal forces generated during high-speed rotation. Quality control was critical, as even minor flaws could lead to catastrophic failure. Standard established dedicated production lines with specialized tooling and inspection procedures to ensure consistency across all units produced. Initial testing of the Hamilton Standard propeller occurred in the autumn of 1943, using a specially modified P-51B as the test platform. The aircraft was instrumented extensively, with equipment to measure propeller thrust, engine power, vibration levels, and structural loads on the propeller blades and mounting hardware. Test flights began conservatively, exploring the propeller's characteristics at normal operating speeds before gradually expanding the performance envelope toward maximum velocity. Early results were promising. The narrow blade design eliminated the severe vibrations that plagued the Aero Products propeller at high speeds. The aircraft accelerated smoothly through 400 miles per hour, with no indication of the turbulence and loss of thrust efficiency that had limited previous attempts. The Critical test came during a maximum performance dive from altitude. Robert Johnson climbed the modified Mustang to 35,000 feet over the test range at Wright Field. At altitude, he rolled inverted and pulled through into a steep dive, advancing the throttle to maximum power. The Mustang accelerated rapidly, the airspeed indicator winding past 350 miles per hour, then 400, then 425. The smooth acceleration continued without the vibrations that typically appeared above 400 miles per hour. Johnson held the dive, monitoring engine instruments and structural indicators. 440 miles per hour, 460. The aircraft remained stable and controllable, 480 miles per hour. The acceleration finally began decreasing as aerodynamic drag increased with the square of velocity, but the propeller continued converting engine power to thrust efficiently. At 490 miles per hour, indicated airspeed, Johnson began recovery from the dive, gradually pulling back on the control column to avoid overstressing the airframe. The Mustang responded smoothly, transitioning from the high-speed dive to level flight without incident. Post-flight examination revealed no damage or unusual wear on the propeller or engine. The Hamilton standard design had successfully pushed the Mustang's maximum speed to levels that made it one of the fastest piston engine fighters in the world. More importantly, the propeller maintained efficiency throughout the speed range, providing excellent acceleration and climb performance, while enabling sustained high-speed flight when needed. The performance gains were quantified through systematic testing over the following weeks. With the standard Aero Products propeller, the P-51B reached a maximum level flight speed of approximately 437 miles per hour at 25,000 feet. With the Hamilton standard propeller, maximum speed increased to approximately 448 miles per hour at the same altitude, a gain of 11 miles per hour. During high-speed dives, the difference was more dramatic. The Hamilton propeller enabled sustained acceleration to speeds exceeding 480 miles per hour, velocities at which the Aero Products design became virtually ineffective due to compressibility losses. The narrow blade design had successfully delayed the onset of shock wave formation, extending the propeller's efficient operating range by approximately 50 miles per hour. The implications extended beyond maximum speed figures. Combat performance depended heavily on acceleration and sustained high-speed capability. Fighter engagements often involved rapid changes in velocity as aircraft maneuvered for position. The ability to accelerate quickly from cruise speed to combat power, maintain high velocity during pursuit or evasion, and recover energy rapidly after maneuvers could determine the outcome of individual encounters. The Hamilton propeller gave Mustang pilots advantages in all these areas. When bounced by enemy fighters, a Mustang pilot could accelerate more rapidly to escape or engage. When pursuing enemy aircraft, the Mustang could sustain higher speeds longer without the performance degradation that occurred with conventional propellers. In turning fights where energy management was critical, the improved acceleration allowed faster recovery of lost speed. Operational testing expanded beyond individual aircraft performance to examine reliability and maintenance requirements under field conditions. The narrow steel blades raised concerns about durability. Some engineers worried that the reduced blade area and thinner cross-sections might prove more susceptible to damage from foreign object impact, particularly small stones or debris kicked up during takeoff and landing on unpaved airfields. Corrosion resistance, if moisture penetrated the blade interior through impact, damage, or seal failures. Hamilton Standard conducted extensive testing to address these concerns, deliberately damaging blades with simulated impacts and exposing them to corrosive environments to evaluate their resistance. Results demonstrated that the Hamilton propeller actually proved more resilient than expected. The steel construction resisted impact damage better than the aluminum alloy blades used on some designs. Small dents or nicks in the blade surface could be smoothed through routine maintenance without requiring blade replacement. The hollow construction, while initially seen as a potential weakness, actually improved damage tolerance. If a blade sustained significant impact damage, the hollow structure would deform locally to absorb energy rather than transmitting the full force to the propeller hub and engine mounting. This characteristic reduced the risk of catastrophic failure propagating through the entire propeller assembly. Manufacturing capacity became the next challenge once testing validated the design. Hamilton Standard operated several facilities capable of producing propellers, but expanding production to meet military requirements demanded substantial investment in new equipment and worker training. The company had been producing approximately 3,000 propellers monthly across all types in early 1943. The Army Air Forces projected requirements for 50,000 or more Hamilton propellers annually to equip new Mustang production and retrofit existing aircraft. Meeting this demand required doubling production capacity within months, while maintaining quality standards that ensured safety and reliability. Hamilton Standard implemented a comprehensive expansion program in late 1943 and early 1944. New stamping presses were installed to form the hollow steel blades. Heat treatment furnaces were added to process the increased blade production. Assembly lines were reconfigured to handle higher throughput while maintaining rigorous inspection procedures. The workforce expanded from approximately 8,000 employees to over 12,000, with new workers receiving intensive training in the specialized manufacturing techniques required for precision propeller production. The company also developed improved quality control methods, including X-ray inspection of blade interiors to detect hidden flaws that might lead to failure in service. By March 1944, Hamilton Standard had achieved production rates exceeding 4,000 propellers monthly, with continued expansion planned to reach 5,000 units by summer. The increased output supported the rapid expansion of P-51 production at North American Aviation's facilities in Inglewood, California, and Dallas, Texas. Every new Mustang rolling off the assembly lines after February 1944 was equipped with the Hamilton Standard propeller as standard equipment. Retrofit programs also began for P-51B and C models already in service, replacing their Aero Products propellers with the improved Hamilton design during routine maintenance or when aircraft returned to depots for modifications. The introduction of the Hamilton propeller coincided with a critical period in the air war over Europe. In early 1944, the 8th Air Force was struggling with heavy bomber losses during deep penetration raids into Germany. Without effective long-range fighter escort, bomber formations faced devastating attacks from German interceptors. The arrival of increased numbers of P-51 Mustangs, equipped with drop tanks, provided the range necessary to escort bombers throughout their missions, but combat performance at high altitude remained critical. German fighters, particularly the Focke-Wulf FW-109 and Messerschmitt Bf-109, were formidable opponents, flown by experienced pilots. Any performance advantage, even marginal improvements in speed or acceleration, could prove decisive in individual combat encounters. The first combat reports filtering back from Europe in April 1944 told a story that performance specifications and test data could never fully capture. Lieutenant Colonel Donald Blakesley, commander of the 4th Fighter Group, submitted detailed assessments after the first missions flown with Hamilton-equipped Mustangs. His pilots had engaged formations of Messerschmitt 109s over central Germany at altitudes above 28,000 feet. The German fighters, flown by experienced pilots from Jagdgeschwader 3, had attempted their standard tactic of diving through the escort screen to attack bomber formations below. Blakesley's Mustangs caught them during the dive. What happened next revealed the practical significance of engineering decisions made months earlier in Connecticut, factories, and Ohio test facilities. The Mustangs accelerated rapidly in pursuit, their Hamilton propellers converting full engine power into thrust even as speeds climbed past 450 miles per hour. The Messerschmitts, equipped with standard propellers optimized for different performance requirements, began experiencing the same compressibility losses that had plagued early Mustang designs. Their acceleration decreased as shock waves formed along propeller blades. The gap closed. Blakesley's pilots achieved firing position and opened fire. 3 German fighters went down in flames. The survivors broke off the attack and fled, abandoning their bomber interception attempt. Similar reports accumulated throughout April and May 1944 as more fighter groups transitioned to Hamilton-equipped Mustangs. The propeller's performance advantages manifested most clearly during high-speed pursuits and diving attacks, precisely the scenarios that dominated fighter combat over Germany. German pilots, accustomed to diving away from pursuing American fighters, with confidence that their opponents would lose ground as speeds increased, discovered that Mustangs now maintained or even closed distance during high-speed runs. The psychological impact was immediate and profound. Luftwaffe tactical doctrine had relied heavily on speed and altitude advantages to offset growing numerical inferiority. When those advantages eroded, German fighter effectiveness declined dramatically. The air was mathematics were brutal and unforgiving. In March 1944, the Luftwaffe lost approximately 160 fighters defending against daylight raids, while claiming approximately 200 to 30 Allied aircraft destroyed, including bombers and escort fighters. By May, after widespread deployment of improved Mustangs with Hamilton propellers and drop tanks enabling full mission escort, German losses had climbed to over 450 fighters monthly, while Allied losses declined to approximately 350 aircraft. The exchange ratio had reversed. The defenders were being destroyed faster than the attackers. At these attrition rates, the Luftwaffe's fighter force was dying. Individual stories from German pilots captured the human dimension behind these statistics. Lieutenant Franz Stiegler, an experienced pilot with Jagdgeschwader 27, described his final combat mission in a post-war interview. Flying a Messerschmitt 109 over Munich in June 1944, he had positioned his formation above an American bomber stream, preparing to dive through the escort screen. As his flight rolled into the attack, Mustangs appeared from above and behind, diving at speeds Stiegler estimated exceeded 480 miles per hour. His own aircraft, already at maximum power, could not match their acceleration. The Mustangs closed rapidly, their superior speed allowing them to achieve firing position before Stiegler's formation could reach the bombers. He saw tracers flash past his canopy, felt impacts along his wing, rolled desperately to evade. 2 of his wingmen died in the first pass. Stiegler managed to escape by diving through clouds, his aircraft trailing smoke from damaged coolant lines. He never flew combat again. The wound to his aircraft was repairable. The wound to his confidence in German fighter capability was not. By summer 1944, the 8th Air Force could dispatch over 1,000 heavy bombers on a single mission, escorted throughout by fighters that matched or exceeded German interceptor performance at all altitudes and speeds. The systematic destruction of German industrial capacity accelerated. Synthetic fuel plants, aircraft factories, ball-bearing facilities, transportation networks. All became targets struck repeatedly with devastating accuracy. German VAR production peaked in July 1944, then began irreversible decline as bombing damage exceeded repair capacity and raw material shortages constrained output. The Hamilton propeller's contribution to this outcome was indirect but measurable. It did not win the war alone. No single component or innovation could claim that distinction, but it solved a specific technical problem at a critical moment, enabling the Mustang to achieve its full potential as an escort fighter. The performance improvements it provided, particularly at high speeds where combat often occurred, gave American pilots advantages they exploited with deadly efficiency. The cumulative effect of thousands of individual combats, each influenced marginally by superior acceleration or sustained high-speed performance, determined the air war's outcome as surely as any strategic decision or operational plan. Fire or watched friends die in burning aircraft. Their contribution was measured in thousandths of an inch tolerances on steel stampings, in airfoil profiles optimized through hundreds of wind tunnel tests, in manufacturing processes refined to produce thousands of identical units with consistent quality. This was industrial warfare fought in factories and laboratories, rather than skies over Germany. The battles were against physics and metallurgy and production schedules, rather than enemy fighters. Yet, victory in these invisible battles enabled victory in the visible ones. Robert Johnson, the test pilot who first pushed a Hamilton-equipped Mustang past 490 miles per hour, never received public recognition comparable to combat aces who scored multiple victories. His name appears in technical reports and test documents, but not in popular histories or memorial plaques. The engineers at Hamilton Standard, who solved the compressibility problem, remain anonymous even in specialized aviation histories. The factory workers who stamped and assembled thousands of propeller blades worked in obscurity, their individual contributions lost in aggregate production statistics. This anonymity characterized the industrial war effort. Millions of people contributed incremental improvements and sustained production that collectively enabled military success, yet most remained unknown outside their immediate communities. The irony was that German engineers understood propeller compressibility problems as well as their American counterparts. Luftwaffe technical staff had conducted extensive research into high-speed propeller design. They possessed the theoretical knowledge and manufacturing capability to produce narrow-blade propellers similar to the Hamilton design. Several experimental propellers with advanced blade profiles were tested on German fighters in 1943 and 1944. Some showed promising results in limited trials. None entered mass production. The reasons were multiple and interconnected. Germany's aircraft industry operated under constant pressure to maximize current production rather than implement improvements requiring production line modifications. Retooling factories to manufacture new propeller designs would temporarily reduce output at a time when every aircraft was desperately needed. Strategic materials, particularly high-quality steel for propeller blades, were increasingly scarce. Existing propeller production consumed available supplies. Expanding output to retrofit existing aircraft with improved propellers was impossible without reducing production of other critical components. Most fundamentally, fuel shortages were grounding increasing numbers of German fighters regardless of their propeller performance. Improving aircraft capability made little sense when insufficient fuel existed to fly the aircraft already available. These constraints revealed the essential difference between American and German approaches to industrial warfare. The United States could afford to temporarily reduce production to implement improvements because total output was sufficient to maintain operational requirements even during transitions. Strategic materials were available in quantities that enabled both current production and future improvements. Research and development efforts could proceed without compromising immediate output because the industrial base was large enough to support both. Germany faced the reverse situation in every category. Each choice involved zero-sum trade-offs, where improving one area required accepting degradation in another. The human cost of these industrial disparities was measured in lives lost and futures erased. Every German pilot shot down by a Mustang, whose performance advantage derived partly from superior propeller design, represented an individual tragedy that resulted from decisions made in factories and planning offices far from the combat. 2. Zone. Every bomber crew that completed their mission, because Escort fighters prevented interceptors from reaching them, owed their survival to engineering decisions about blade width and airfoil profiles. The connection between technical choices and human outcomes was absolute and direct, yet invisible to most participants. Lieutenant Hans-Joachim Marseille, one of Germany's highest-scoring fighter aces with 158 confirmed victories, was killed in September 1942 when his Messerschmitt 109 suffered engine failure during a return flight from a combat mission. The cause was eventually traced to contaminated fuel that damaged cylinder heads. The contamination resulted from inadequate quality control at a synthetic fuel plant operating beyond designed capacity to meet desperate demand for aviation fuel. The plant was operating at maximum output because previous facilities had been destroyed by Allied bombing. The bombing had been possible because German fighters lacked fuel reserves to mount sustained defensive operations. The fuel shortage existed because synthetic production could not replace natural petroleum sources lost when Germany failed to secure Middle Eastern oil fields. Every link in this chain of causation connected back to industrial capacity and resource availability. Marseille's skill and courage could not overcome the systemic constraints that ultimately killed him. The same logic applied to Allied personnel, though the resource equation favored them. American pilots died when their aircraft suffered mechanical failures, when they were shot down by skilled German opponents, when they made tactical errors, or encountered situations where superior enemy numbers overwhelmed individual performance advantages. But American losses occurred against a background of sustainability. Replacement pilots arrived from training schools at rates exceeding combat losses. Replacement aircraft flowed from factories faster than they were destroyed. Mechanical failures decreased as production quality improved and engineering problems were systematically resolved. The industrial system supported the combat forces rather than constraining them. By autumn 1944, the Luftwaffe was destroyed as an effective fighting force. Operational fighter strength had declined to approximately 1,000 aircraft, down from over 2,000 in January. Pilot quality had collapsed, as experienced aviators were killed faster than they could be replaced, and replacement pilots arrived with minimal training. Fuel shortages meant that many aircraft sat idle on airfields, unable to fly combat missions. The few sorties that were flown achieved little against overwhelming Allied numerical superiority and qualitative parity or superiority in equipment performance. The final missions of the European air were in April and May. 1945 were almost anticlimactic. Allied fighters roamed freely over Germany, attacking targets of opportunity without encountering meaningful resistance. The Mustangs that had fought desperate battles over Berlin in March 1944 now escorted bombers to targets deep in what remained of the Reich without seeing enemy fighters. The propellers that had been carefully optimized to provide high-speed performance advantages spun in air empty of opponents. Victory had been achieved so completely that the tools designed to enable it were no longer necessary. The post-war accounting revealed the scale of the air campaign's destructive power. Germany had produced approximately 40,000 fighter aircraft during the war years. Approximately 25,000 were destroyed in combat or accidents. The Luftwaffe lost approximately 50,000 aircrew killed, representing nearly 70% of all personnel who served in fighter units. These losses included some of Germany's most talented and experienced pilots, men whose skills had been developed over years of training and combat. but who could not overcome the mathematical certainty of sustained attrition warfare against numerically superior opponents. The 8th Air Force alone lost approximately 6,000 aircraft and 47,000 aircrew during the strategic bombing campaign. These numbers represented genuine tragedy for the families and communities from which these men came. Yet from the industrial warfare perspective, these losses could be absorbed. American aircraft production exceeded 60,000 fighters during the war years. Pilot training schools graduated sufficient numbers to replace losses and expand force size simultaneously. The system could sustain operational tempo indefinitely because production exceeded consumption. The Hamilton Standard propeller remained in service long after the war ended. Mustangs, equipped with these propellers, flew combat missions in Korea from 1950 to 1953, primarily in ground attack roles where their speed and range remained valuable. Air forces around the world operated Mustangs into the 1980s in some cases, testament to the design's fundamental soundness. The propellers themselves proved remarkably durable, with many units accumulating thousands of flight hours without requiring major overhauls. Some examples remain in service today on vintage aircraft maintained by collectors and museums. The broader legacy extends beyond the specific hardware to the principles it represented. The Hamilton propeller demonstrated that systematic engineering could solve complex technical problems through methodical analysis and testing. It showed that manufacturing quality and consistency mattered as much as theoretical performance. It proved that marginal advantages in individual components could accumulate into decisive superiority when multiplied across thousands of units engaged in sustained operations. These lessons influenced post-war military procurement and development, establishing standards for how advanced weapons systems should be designed, tested, and produced. The story also illustrates the essential role of industrial capacity in modern warfare. Technical innovation matters, but only if it can be produced in sufficient quantities to affect operational outcomes. Germany possessed talented engineers and advanced technology in many fields, yet lost the war because their industrial base could not sustain the material consumption rate that modern combat demanded. The United States won not primarily because of superior individual weapons, though American equipment was generally excellent, but because American industry could produce adequate weapons in overwhelming quantities, while simultaneously supporting research and development of improvements. Walking through aviation museums today, visitors can examine preserved P-51 Mustangs displayed with their original Hamilton Standard propellers. The narrow, steel blades show wear patterns from decades of use, testament to their durability. Information placards describe the propeller's technical specifications and note its contribution to the Mustang's performance. What they cannot fully convey is the human dimension. The lives saved because Escort fighters could protect bomber crews, the lives lost because defenders could not overcome the advantages these propellers helped provide. The hardware is visible and measurable. The human cost remains abstract, even when documented in statistics. The engineers who designed the Hamilton propeller made choices based on aerodynamic principles and manufacturing constraints. They optimized blade profiles to delay shock wave formation. They selected materials that balanced strength against weight. They designed production processes that enabled mass manufacturing while maintaining quality. These were technical decisions made using mathematics and test data, rippled through the combat forces that depended on their work. Every increment of improved performance translated into marginally better survival odds for friendly pilots and marginally worse odds for enemy opponents. Accumulated across thousands of sorties and hundreds of thousands of flight hours, these marginal differences determined who lived and who died. The final assessment must acknowledge both triumph and tragedy. The Hamilton propeller succeeded brilliantly at its intended purpose. It solved the compressibility problem that limited Mustang high-speed performance. It enabled the aircraft to achieve its full potential as an escort fighter. It contributed measurably to Allied victory in the air war over Europe. This is historical fact, supported by documentary evidence and combat records. But that victory came at a cost measured in destroyed cities, in millions of military and civilian dead, in a generation scarred by trauma and loss. The propeller was a tool used in pursuit of dome, necessary victory over an evil that threatened civilization itself. Recognizing its effectiveness does not require celebrating the circumstances that made it necessary. 80 years removed from these events, we can examine the Hamilton Standard propeller as an artifact of a particular moment in history when industrial capacity and technical innovation combined to decisive effect. We can appreciate the engineering sophistication it represented and acknowledge the human skill required to design and manufacture it. We can recognize its contribution to victory in a war that needed to be won. And we can remember that behind every technical specification and performance improvement were young men flying in combat, some who came home and some who did not, all of whom served causes larger than themselves in a conflict whose outcome shaped the world we inherited. The narrow steel blades spinning at high speed converted mechanical power into thrust that carried fighters into battle. What they carried forward was not just aircraft, but the hopes and fears and courage of the men who flew them and the nations that sent them. That human dimension gives meaning to the technical achievement and reminds us that history is ultimately about people, not hardware. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.